Hello and welcome to the 21st lecture of our course on photonic devices. On today's lecture, we're going to start discussing photodiodes, and in particular, we'll define some important parameters relating to photodiodes, such as the responsivity, the response time, and the quantum efficiency. The detectors usually used in optical communications are photoconductive devices. So you could also have another class of detectors which are photoemissive devices such as photomultiplier tubes, but these are not usually used in optical communications. But in the photoconductive devices, the conductivity of the usually semiconductor device is modified with the incidence of photons. So usually you have some sort of device with electrical contacts, and it's usually made of a semiconductor. So these would be the metallic contacts, and with the incidence of light, right, with the incidence of photons, the conductivity of the material or device is changed so that these optical power can be translated into a current, right, which we can measure. So therefore we can relate this current with the incident optical power and therefore measure the incident optical power through the current. Now, as we've said, most of the photoconductive detectors are made up of semiconductors, and the devices themselves can be photoconductors, which do not require any type of PN junction or PIN junction or anything like that, right? So in these devices you just have a piece of semiconductor, and because of absorption and carrier generation, the incidence of photons will generate more carriers and change the resistivity or the conductivity of the device. On the other hand, you can have photodiodes, and these can be PIN. So here you have a sandwich with a p-type, an intrinsic, and an n-type semiconductor. So this is a type of photodiode, or avalanche photodiodes, APD, which usually are used to make ultra-fast detectors, and we'll take a look at these as well. And we'll focus on this class of detectors, right? And you can also have phototransistors, which will also not be the focus of this couple of lectures. And as we've stated, these devices are based on photon absorption, right? Because as we've seen, in the process of stimulated absorption in a semiconductor, you usually what you have is an electron sitting down in the valence band, and then with the incidence of a photon which is absorbed and therefore annihilated, right, with a given energy equals to hf, the electron can gain energy and transition up into the conduction band, into an empty state in the conduction band, so that at the end of the process the electron is actually sitting up here. It has gained energy, and the energy has been provided by the photon, which at the end of the process is annihilated, right? But note that at the end of this process, what you have is an empty state down here in the valence band, because the electron has moved up in energy, and an electron in the conduction band. So the process of absorption, right, is directly related to the process of carrier generation, because at the end of this process we've generated an electron in the conduction band, which can be used to conduct electricity, and also a hole in the valence band, which can also be used to conduct electricity. So there are a few different parameters which can be used to characterize photodiodes, right? And the most important ones are the quantum efficiency, eta, which is different than the intrinsic efficiencies in the light sources that we've seen, the LEDs and lasers, okay? The responsivity of the device, right, which is going to characterize the relationship between the generated current, the photocurrent, and the incident optical power. So this is a key parameter. the response time, which is going to determine the frequency or the speed, the rate with which the detector can operate, the maximum speed, so the response time, and also the dark current, which is the current in the absence of impinging photons, in the absence of light. Well, the quantum efficiency is the ratio of the electron-hole pairs available for current conduction per incident photon. So this is the definition of quantum efficiency. So it's the ratio of the generated electron-hole pairs, which can be converted into a photocurrent. Okay, so let's remember the basic picture that we have here. We have a device in which the incidence of photons, the incidence of light with given amount of power, will generate electrons and holes, and these electrons and holes, in the presence of an electric field, for example, move inside the device and therefore constitute an electrical current. Now this electrical current will give us information about the incident optical power. So the quantum efficiency is the ratio of the amount of generated electron-hole pairs available for current conduction per incident photon of light. And in order to define the quantum efficiency, we need two parameters. The first one is the photon rate, which is just the number of photons incident on the device, right, per unit time. So usually the information that we have associated with a light beam, for example, is the power of the light beam. So you have a given optical power, let's call this P light, for example, that we want to know. We want to find out the amount of power which is in watts, which is impinging on the device. But how can we define then the photon rate, the number of photons per unit time, right? Well, as we've seen, if we divide the impinging light power by the energy of a single photon, we'll get the photon flux or the photon rate, right? The number of photons which are impinging on the device per second or per unit time is obtained in this way, by dividing the optical power by the energy of a single photon, which is this quantity right here, right? So if this is in joules, because it's equal to energy, and this is given in watts, which is joules per second, we can easily see where this comes from, right? Because since this is since power is the amount of joules, the amount of energy per unit time, and we divide this by the energy of a single photon, then we can find out the number of photons per unit time which is impinging on the device associated with a given amount of power. Okay, this would be the photon rate in units of per second. Now the rate of carriers that contribute to the photocurrent, which goes in the numerator of the expression for the quantum efficiency, can be found by the photocurrent itself, by the current which is produced in the device, right? So because of the electron hole pairs that are generated in the presence of an electric field, a photocurrent or current can be generated, and the rate of electrons and holes, or the rate of carriers that contribute to photocurrent, is just this current divided by the charge, the absolute value of the charge of the elementary charge, or the charge of the electron, right? Because again, this is given in amps, which is equal to coulombs per second, so charge per unit time. This is the charge of a single electron in coulombs, and therefore if we divide this, which is the charge per unit time crossing the cross-sectional area of a wire, by the charge of a single electron, we find the number of carriers, the number of electrons and holes which are crossing the cross-sectional area of the wire or the semiconductor per unit time. Okay, so this will give us the number of electrons or holes per unit time associated with the photocurrent. So this is the rate of carriers, also given in units of per unit time or per second. So now in order to find the quantum efficiency, we just have to divide the rate of carriers by the photon rate, right? The rate of carriers we found to be the photocurrent divided by the elementary charge, and the photon rate is the light power of the impinging beam divided by the energy of a single photon. And if we rearrange things, we obtain this expression here. Therefore, the quantum efficiency is IP times HF divided by the light power multiplied by the elementary charge. And quantum efficiencies can have values that are between 0 and 1, right? And what does this mean, right? So in the process of carrier generation by absorption, right? So again, right, we have a absorption of light with energy HF, which generates an electron hole pair because the electron gains energy and rises up to the conduction band. And if every photon here that impinges on the device generates an electron hole pair, and every electron hole pair generated is actually used in order to make up the current through the device, then you would have a quantum efficiency of 100%, or eta equals to 1, right? On the other hand, you know, if of all of the impinging photons, none of them were able to generate electron hole pairs which were actually used in order to make up the photocurrent, then the quantum efficiency would be 0. So it's clear that eta is going to be a number between 0 and 1, an efficiency parameter in this range, because it gives us the efficiency of the material or device in being able to translate the number of impinging photons into an actual generation of electron hole pairs which can be used to conduct electricity, right? Now, another important parameter that we've already mentioned and is sort of related to the quantum efficiency is the responsivity of the device, right? The responsivity of an LED, we've looked at this before, because the LED is usually going to be made up of a junction, right, a PN junction, in which is of course forward biased, and therefore you'll have a direct bias current here. And well, the LED, the active region of the LED, be it a PN junction or a DHS, is gonna emit light, right? So it's gonna emit light, it's gonna emit photons, and therefore the responsivity here would be defined as the power, the emitted power divided by the direct current, right? So in watts per amps. So therefore the responsivity is power over current in this case, right? Because you're taking a current and turning it into an emitted beam of light, and therefore you want a parameter that can give you an efficiency in terms of how much optical power is emitted per unit current. So it makes sense that the responsivity has to be this. In photodiodes, on the other hand, the responsivity is a different quantity, although it has the same name, right? Quantifies the ability of the detector to convert light power into electrical current, and not the other way around, which is the case for optical sources, right? So, the ability of the device to convert the incident power, the incident optical power, into a photocurrent. And therefore, it only makes sense that the responsivity is going to be the photocurrent divided by the incident optical power. Okay, so again, if the device is sitting here and you have an incident optical power which is going to generate electron hole pairs which are going to be converted into a photocurrent. Then you want an efficiency parameter, which is going to give us the amount of current, of photocurrent generated per unit optical power, right, in amps per watt. And typical values for the responsivity associated with photodetectors, photodiodes, is around a half an amp per watt, right? So 500 milliamps per watt. Now, considering that the expression that we've obtained for the quantum efficiency was this, right, IP over the optical power times HF over E, we can readily identify this term here as being the responsivity for photodetectors that we've just defined. So therefore, eta is going to be equal to R, the responsivity, times HF over E, right, just from this expression. And if we isolate the responsivity here and, you know, pass this term to the other side, we can express the responsivity in this way, right? So the responsivity will be eta times E over HF. We can also express this, instead of as a function of frequency, we can use the fact that F times lambda naught is equal to C and express this in terms of the wavelength rather than the frequency of the light beam. Therefore, and this will give us eta times E multiplied by lambda naught. So this is just the wavelength in free space, right? The wavelength of the optical electromagnetic radiation impinging on the device, which we want to detect the power of, divided by Planck constant multiplied by the speed of light in vacuum. Okay, and if we substitute all of the constants here, we can find this useful expression which gives us the responsivity in terms of the wavelength and the quantum efficiency only. So the responsivity is equal to eta multiplied by lambda naught in micrometers, right? So you, for example, if this corresponds to red light, so 0.632 microns, you would use just 0.632 and leave off the micrometers, right? So eta times the wavelength in micrometers divided by 1.24 amps per watt, right? So this is a very useful expression. If you have the quantum efficiency and the wavelength of the optical beam impinging on the device in micrometers, you can readily find the responsivity using this expression. And from this expression, we can see that in order to increase the responsivity, what we want is to maximize the quantum efficiency, right, for a given frequency or wavelength of optical beam impinging on the device. And there are different reasons which can make the quantum efficiency, not to be 100%. So the first one is the fact that if you have a given device here, right? So if you have a piece of semiconductor in any given configuration, which we'll look at later, right? And there is an optical beam, right, with a given power impinging on the device, part of this optical power can be lost right at the interface because it would be reflected, right? So if you multiply the reflectivity by the optical power, you get the amount of light which is reflected at the interface, just because there is a refractive index difference right at the interface, right? So for example, you could have air as an outside medium, so the refractive index on this side would be in air, which is 1, and the refractive index of most semiconductors is around 3.4, right? So you have a refractive index difference which can induce a reflectivity which is different than 0, right? So which would mean that part of the light beam would be reflected and not go inside the device, and therefore it would not be able to, that fraction of the optical power would not be able to be used to generate electron hole pairs and eventually be transformed into a photocurrent, right? So from the phi naught photons per second that impinge on the detector, a fraction is transmitted through the air semiconductor interface, and another fraction is reflected. The fraction that is transmitted is equal to the transmittance, right? The fraction of that is reflected is equal to the reflectance. So in the transmittance is equal to 1 minus the reflectivity, and the transmittivity is equal to 1 minus the reflectivity. Actually, the correct terms here would be transmittivity and reflectivity. This has to be taken into account, right? Only a fraction equals to t of the incident photons will actually enter the device, and will actually potentially be used in order to generate electron hole pair. Now, if you have the piece of semiconductor here, and you have a given photon rate phi naught, which is the number of photons per second impinging on the semiconductor, we just saw that a fraction is going to be reflected and only a fraction is going to be transmitted to the interior of the semiconductor. So this fraction, which is actually transmitted to the inside of the semiconductor, is this right here, right? So let's point out that this is the number of photons per second which actually enter the device. Once the photons are inside the device, some of them will be absorbed at a given rate, and if we look at the photon rate as a function of distance along the length of the light beam as it travels inside the device, it's only logical to expect that the photon rate will drop exponentially, right? Because the photons will be absorbed. So the photon rate which actually enters the device will behave like this, right? Phi multiplied by e to the power of minus alpha z, or alpha x in our case here, right? And alpha here is just the attenuation constant associated with absorption, so alpha of the material. So just like the optical power, the photon rate will drop exponentially in this fashion right here. And if we look at the photon rate at a given distance of the interface, so let's say a distance d along the x direction, the photon rate is gonna drop to what? Right here the photon rate will be phi multiplied by e to the power of minus alpha times the propagated distance d. Does this make sense? So the photon rate is going to drop exponentially, and at a distance d from the interface it's going to have this value, assuming that phi is the photon rate right at the right side of the interface, right, when the beam has actually entered the device. So but what we're actually interested in is the amount of absorbed photons at a given distance d from the surface, right? Because the absorbed photons are the ones that are going to be generating the electron hole pairs. We can find this by considering the following, right? If this is the number of photons per second which actually enter the device, if we multiply this by 1 minus e to the power of minus alpha d, we find the amount of absorbed photons at a distance d, right? If we took this quantity right here, phi naught multiplied by 1 minus r multiplied by e to the power of minus alpha d, we would actually find the photon rate which is not absorbed, which is actually propagating inside the material at a distance d from the interface. But what we want is the complement of this, so the amount of photons which are per unit second which are actually absorbed by the device, not the amount of photons which are not absorbed and propagating inside the device, but the amount of photons which are actually absorbed by the material, and this would be this quantity here, right? So the complement of this, right? 1 minus this multiplied by the initial amount of photons. Now, since this gives us the amount of absorbed photons at a distance d from the surface, from the interface, we can use this in order to find a more specialized expression for the quantum efficiency. Okay, but there's a third factor which has to be taken into account, right? So the first one is the reflectivity at the interface. The second one is the actual absorption along the material. So the optical power or the photon rate is going to decay exponentially along the length of the material, the length of the beam. But also from all of the absorbed photons, a fraction of them may not contribute to photocurrent generation due to different factors, right? So some of the photons which are actually absorbed, the energy of these photons, rather than generating, being used to generate electron hole pairs, it can be used to some other purpose. For example, this energy associated with the photon can be converted into phonons or into vibrational energy, modes of vibrational energy of the crystal lattice, basically be converted into temperature, and therefore not be used to generate electron hole pairs. So some of the photons can be lost in this way. Also, non-radiative recombination of the electron hole pairs can happen before the electron hole pairs actually get to the electrode. So considering the following scenario, right? We have the device here, and a given photon impinges on the device here and is actually able to generate an electron in the conduction band and a hole in the valence band. And if you polarize the device, right, in some way that we're going to look at later, these electron and hole can be put into motion, right? So if the electric field is to the right, the hole would move in the direction of the electric field and the electron would move in the opposite direction, and this would potentially constitute an electrical current right here. But what can also happen is that in traveling along the device, this electron can recombine with a different hole, and this hole can recombine with a different electron, and therefore this before they would get to the electrodes at either end here, they could recombine, and in that case they would not contribute to the photocurrent at all, right? They would not contribute to the photocurrent at all. So if recombination takes place, some of the generated electron hole pairs, electrons and holes, can be lost, right? So this is another factor, another phenomenon which contributes to the decrease of the photocurrent, to the loss of efficiency in converting the impinging photons into a photocurrent. Okay, taking all of these phenomena into account, the fraction of absorbed photons that actually contribute to the current we can call lowercase zeta, right? Lowercase zeta. So this parameter here is the fraction of the absorbed photons which actually contribute to the photocurrent, because the associated electron hole pairs which are generated are actually generated, right? The photon is not used in order to, is not converted into a phonon, for example, and once they're generated, they do not recombine along the length of the material. So they actually contribute to the photocurrent. So the fraction of absorbed photons that actually contribute to the current we'll call zeta, and this is another efficiency parameter, right? Which will be between 0 and 1. If it's 1, this means that all of the impinging photons are used to generate electron hole pairs which do not recombine and actually constitute the photocurrent. If it's 0%, this means that of all of the impinging photons, none of them will be converted into a photocurrent by carrier generation. So taking all of these factors into account, the quantum efficiency which is the fractional amount of electrons and holes available for current conduction per incident photon, will be all of these terms in the numerator here multiplied by the incident photon rate, right? So again, what does this mean? So these terms in the numerator take into account all of these loss factors in the conversion of the photon rate into a photocurrent. So for example, if this is the incident photon rate, this quantity, as we've seen, is the actual photon rate which enters the device through the interface with air, right? And this term here gives us the fraction of this which is actually absorbed by the material, right? Because in order to generate electron hole pairs, the photons need to be absorbed. So this right here is the fraction of photons which are actually absorbed at a distance d from the interface, and this parameter here is the fraction of absorbed photons which are actually converted into a photocurrent. And the reason that they would not be is what we just said, right? Some of the photons could be converted into phonons, into temperature, or they could recombine after being generated inside the device, right? If you consider all of these loss mechanisms, the reflection, the fraction that is absorbed, and the fraction that is not absorbed, and loss due to recombination, and so on, the quantum efficiency will be this divided by the actual photon rate impinging on the device. So this cancels out this guy right here, and we see that eta is 1 minus r multiplied by 1 minus e to the power of minus alpha d multiplied by zeta, right? So this is a more specialized expression for the quantum efficiency, which takes into account reflection, absorption, and the efficiency zeta. And by looking at this expression and noting how it was derived, we see that the quantum efficiency can be increased by, for example, using anti-reflective layers on the surface of the device, right? So if, for example, for the operating wavelength, we deposited some anti-reflective coating films right at this surface, which would prevent light at that specific wavelength from being reflected, so guaranteeing that all of the light at this wavelength is actually transmitted into the device. Then we can increase the quantum efficiency, because we'd be virtually turning this term here into 1, right? Because the reflectivity would be 0. Also, if we choose a material with a proper alpha attenuation constant, so for example, indium gallium arsenide is a material which is typically used in optical communication wavelengths or frequencies, because it has an adequate attenuation constant for the related wavelengths. And we can also design properly the length of the device, so the length in which the light beam is going to propagate inside the device, in order to make this term right here close to 1, right? So what we want is this to be close to 1, as close as possible to 1, and this term right here also close to 1, and this third term right here close to 1. And in order to make this term as close as possible to unity, we can choose the right material with the right attenuation constant and design the length of the device adequately, right? And last but not least, we can use a good quality semiconductor with few defects in the crystal lattice, because these defects will potentially cause more recombinations, or increase the recombination rate, recombination per unit time. And if we use a good quality semiconductors, we can make this term as close to unity as possible as well, right? So hopefully this gives us an idea of the different effects, right, in decreasing the quantum efficiency, and how we can proceed in order to design the device in order to increase it and have high quality photodetectors or photodiodes.